There is a highly specific sensory ideal when it comes to comfort food. It starts with a shatteringly crisp exterior that gives way to a hot, gravity-defying strand of melted cheese. But if you've ever tried to make fried mac and cheese at home, you've likely encountered a much grimmer reality. The bite either explodes into a greasy, oily mess in the pan, or you bite into it only to find a dry, crumbly center. You can't achieve that perfect, stretchy texture by simply mixing noodles, cheese, and breadcrumbs together. Treating the recipe as a simple list of ingredients often leads to the structural collapse of the bite before the center even melts. To get that perfect pull, we have to reverse engineer the bite layer by layer. We need to look at how microscopic proteins behave under stress, the effects of extreme temperatures, and the structural physics of breading. Success in the kitchen depends on how well we manage these invisible factors. By deconstructing the bite, we can see how thermodynamics and protein chemistry dictate the final texture. Let's start at the absolute center of the bite. The primary mechanical challenge here is engineering that dramatic, unbreakable stretch when the food is pulled apart. This diagram illustrates casein, the primary protein found in milk. When cheese is heated, these casein proteins unravel and form a flexible, interlocking web. This biological net traps floating fat and moisture particles, allowing the cheese to bend and stretch without snapping. Young, high-moisture cheeses like mozzarella are packed with water. Because they are still fresh and pliable, their casein network is loose. It easily bends and pulls when exposed to heat. Over time, cheese loses that moisture. The casein network in an aged cheddar or Parmesan becomes incredibly rigid. When heated, instead of stretching, those rigid protein bonds snap and the cheese crumbles into a pool of separated oil. This brings us to the danger of the second cook. By taking macaroni and cheese and deep frying it, you're subjecting it to a second round of intense heat. That heat will evaporate the remaining interior moisture, leaving you with a dry core and no stretch. Two specific adjustments can safeguard this moisture. First, you can add 30 to 50% more liquid cheese sauce to your mix than you normally would. Or you can introduce a compound called sodium citrate, a salt that forces the cheese to emulsify and retain its elasticity even under extreme heat. But having the right internal chemistry doesn't matter if you ignore the physics of the fry. Dropping a room temperature ball of macaroni into a vat of boiling oil guarantees the entire structure will fall apart before a crust can even form. You have to physically freeze the macaroni bites before breading them. This creates a thermal time delay during the cooking process. That frozen core acts as a temporary thermal shield. It keeps the delicate casein network safe and insulated on the inside, while the violent, high-heat cooking solidifies the exterior. Moving outward to the crust layer, we hit the protective barrier. A standard breading station uses flour to absorb surface moisture, an egg wash as a binder, and an outer layer of breadcrumbs. Look at this cross-section comparing traditional breadcrumbs to panko. Traditional crumbs are made from whole bread and have a dense, round shape that absorbs cooking oil like a sponge. Panko is made entirely from crustless white bread, giving it a flaky, elongated structure that tends to repel the grease, keeping the exterior light and crisp. This diagram outlines the thermal catalyst for our reaction, the deep fryer. To safely bridge the gap between a frozen core and a crispy shell, the oil must remain in a strict window between 350 and 375 degrees Fahrenheit. Drop the temperature too low and the crust takes too long to seal, allowing the egg and flour to dissolve into the oil. Spike the heat too high, and the panko barrier will burn before the frozen center has a chance to thaw. Even with perfect breading, the chemistry of the oil itself evolves over time. As oil is reused, it breaks down and generates polar materials, which alter how efficiently the liquid conducts heat to the surface of the food. You can identify this degradation by a dark, murky color and the buildup of foam on the surface. Frying in this environment results in a greasy, soggy crust, regardless of how well the bite was assembled. Deep frying is an unforgiving thermal reaction. It only succeeds if the panko barrier and the cooking medium are perfectly calibrated. Once the bite leaves the oil, the cooking process doesn't stop. The internal chemical reaction remains active during the resting phase. It might seem logical to break the bite open while it's still piping hot, but doing so will ruin the stretch. At peak heat, the casein proteins are too liquid. Pull them apart now, and the strands will immediately break. As this diagram shows, you have to let the internal temperature drop. When it reaches a specific window between 140 and 158 degrees Fahrenheit, the liquid casein web begins to cool and partially solidify, tightening into thick, highly elastic bands. Only at this exact thermal sweet spot do you achieve the final payoff, a massive, elongated pull of cheese that stretches continuously without breaking. Achieving this specific sensory experience is never a matter of luck in the kitchen. It is the deliberate, predictable result of managing thermal dynamics and protein chemistry correctly.